Hello everybody. Welcome to the lecture series Foundation for VLSI Design. This is the 7th lecture. In this lecture, we'll be looking into MOSFETs. Specifically, in this lecture, we'll be looking into types of MOSFET, the operating regions in a MOSFET, some short channel effects, and how a MOSFET can be used as a switch. So MOSFETs are of two types. The first one is N-channel MOSFET or NMOS. So in an NMOS, the current transport occurs mostly because of the electrons. And in a P-channel, the other type of MOSFET is the P-channel MOSFET or PMOS in short. And in a PMOS, the current transport occurs because of holes. Now let us look into the structure of an NMOS or N-channel MOSFET. So in an N-channel MOSFET, we have source and drain, which are heavily doped N-type region or N plus region, right? So this is the source, this is the drain. So the doping in concentration in the source and drain is high, right? So source and drain work as a contacts in a MOSFET, and the body or the substrate is p-type, right? So note that the doping of drain and source is opposite of the body or the substrate, right? So the substrate is of p-type. So if we have n plus region and p-type region, then along at the boundary we'll have depletion region. So we had looked into the p-n junction. So whenever there is a p and n type material, so at the boundary between them, there will be a depletion region, right? So a depletion region will be found in between the n plus source and the p type substrate, and n plus drain and p type substrate. And then there is a gate oxide, right, which is sandwiched, or which is lying between the gate metal and the p-type substrate. So gate oxide is a an insulator, right? So gate oxide can be either silicon dioxide or high K dielectric material, such as, say, for example, hafnium dioxide. So that can be the gate oxide material, and it is an insulator, right? And the gate electrode, or it can be either metal or it can be doped polysilicon, right? So it can be either p plus poly or the n plus poly, right? So now we can see in this case that the MOSFET is formed, or MOS structure is formed. So what is MOSFET, or what is the full form of MOSFET? MOSFET is short for metal oxide semiconductor, right? So this is basically the MOS, and then FET stands for field effect transistor. So we can see that in this structure there is a MOS structure, right? So the metal is there, then oxide, which is an insulator, and then the semiconductor, and that's why it is known as a MOSFET, right? What is field effect, we'll see later, right? So if we consider the other type of MOSFET, that is the p-channel MOSFET or PMOS, the structure is similar. The differences are that instead of the drain and source being n plus, it will be p plus, right? So it will be rich in holes rather than electrons, right? So again, in PMOS, the source and drain acts as contact, meaning that through which the current will get in the transistor and get out of the transistor, or electrons and holes, or the carriers, will be actually going inside the MOSFET and being removed from the MOSFET. So the carriers or the terminal which injects carrier, or is the source of the carrier in the MOSFET, is known as the source, right? And the terminal which takes out or removes the carrier from the transistor is considered the drain, right? So if we consider an NMOS, right? So in NMOS we said that the current flow occurs because of electrons. So the in an NMOS, the source will inject electrons inside the transistor, right? So electrons will go inside through the source and will leave through the drain, right? So note that the conventional direction of current is in opposite to the direction of flow of the electrons. So the current will flow from drain to source, right? Why the current will flow, those things we'll see later, right? And in a p-type MOSFET or PMOS, the source is the terminal through which holes get injected into the transistor, right? So hole will enter the transistor through the source in a PMOS and will leave the transistor through the drain terminal, and the direction of the current will be the same as the direction of the movement of the holes, right? So the now let us look into that how the MOSFET behaves and so on. So the heart of the MOSFET is the MOS capacitor, right? So this MOS capacitor basically behaves similar to a parallel plate capacitor. So let us understand that where in this MOSFET is the MOS capacitor and why does it behave like a parallel plate capacitor, right? So remember from say high school's courses that there is a the parallel plate capacitor has two metallic parallel plates, right? And between them there is an insulator material on, and this is constitutes a parallel plate capacitor, right? Now similar to the parallel plate capacitor, we have a capacitor in the MOSFET. So the one of the terminals of of this parallel plate capacitor is the gate metal, right? So the metal can be considered as one of the plates, and the other plate is the rather than a metal plate, it is the substrate, right? So or the semiconductor. So the semiconductor is acting as the second parallel plate, and between them there is the gate oxide, that is either silicon dioxide or hafnium dioxide, that is basically the insulator. So now how can we say that the semiconductor or the substrate is acting as a as a metal plate, right? So that can happen if we consider that if the concentration of electrons or holes in the substrate is very high. Suppose that condition is reached, right? So suppose there was lot of electrons in the substrate at the surface, right? So in that case we can consider that this semiconductor is behaving more like a conductor, right? Why it is behaving like a conductor? Because it has got lots of carriers, so it is a good its conductivity is very high, and therefore we can consider this the semiconductor or substrate at the surface where the electron concent or hole concentration is very high, that can be considered as a metal plate, right? And in that case we can consider this structure as as similar to a parallel plate capacitor, right? Now how can we have a very high concentration of electrons or holes in a semiconductor? We can achieve that, or we can obtain a very high concentration of electrons and holes at the surface by applying voltage at the gate terminal, right? So when we apply voltage at the gate terminal, an electric field is created in this direction, right? An electric field is created in this direction, and its direction will be dependent on whether we apply positive voltage or the negative voltage, but it will be perpendicular to the surface, right? To the semiconductor surface, right? So the electric field which is created by the gate on application of voltage will lead to accumulation of carriers at the surface of the semiconductor, right? For example, if we have we apply a negative voltage, if we apply negative voltage to the gate, and this is a p-type substrate, in that case holes will get attracted towards the surface and will get accumulated in this region and will have high concentration of holes, right? Similarly, if we have lots of we apply a high positive voltage to the gate, right? In that case the electrons will get attracted towards the surface and the holes will repelled away, right? So at the surface we'll have a lot of or a very high concentration of electrons, and therefore the conductivity of the substrate will be become very high, right? So when voltage is applied to the gate, the concentration of carriers in the semiconductor changes due to the field effect, right? So the field effect is basically when we apply the voltage and an electric field is created in the direction perpendicular to the semiconductor surface, right? And it leads to change in the or the modulation of the conductivity of the substrate. This effect is known as the field effect, right? So the MOSFET works on field effect, right? And that's why there is the word, or in the MOSFET, in the full form of MOSFET we have FET. So this FET represent field effect transistor. Why we call MOSFET? Why, what is the relevance of field effect in the MOSFET? The relevance is that the field effects actually modulates the conductivity of the substrate, and that forms the basic operating principle of a MOSFET. Now, when gate voltage is sufficiently high and there is a quantity which is known as the threshold voltage. So in a NMOS, if the gate voltage is sufficiently high than the threshold voltage, right, then what happens? In that case, the high concentration of electrons will be formed just below the gate, and this thin layer of charge is called the channel, right? So when we apply a positive voltage and this voltage Vg is greater than the threshold voltage Vt, let's call this threshold voltage as Vtn, right? That this is the symbol that we have used here. So if it is greater than Vtn, right, in that case at the surface there will be lots of electrons or very high concentration of electrons, and the conductivity of this at the surface will be very high, right, compared to when no voltage was applied to the gate. So this thin layer of charge is known as channel. So when we apply gate voltage greater than the threshold voltage, we say that the channel has formed at the surface, right? Now if we apply voltage across the drain and source, a current will flow, right? So earlier if there was no voltage, we had at the in between the N plus and substrate, we had the depletion region. Here also we had the depletion region. But when we applied the voltage, positive voltage to the gate, and high concentration of electron is formed, right? So we have now a continuous region of high electrons, right, from the drain to the source through the channel, right? So channel has electrons, lots of electrons. So there is a region of very high concentration of electrons between the source and drain. And now if we apply a voltage between drain and source, then electrons will be injected through the source and through the channel it will reach the drain, right? So this is how the current will flow, right? So if a voltage is now applied to drain and source, when the gate voltage is greater than Vtn, then the current will flow between drain and source. So when gate voltage is lower than Vtn, right? So when there was no positive voltage, in that case, then no significant current will flow, right? So even we apply voltage between drain and source, since in this region we don't have much concentration of electrons and holes, and also there is a depletion region between the source and the substrate, right? So the current will not flow, right? So PMOS works analogously. So here we have shown only the NMOS. The in PMOS works in a similar manner. Only thing is that the channel will be formed of holes rather than the electrons in a PMOS. Now, what are various operating regions in a MOSFET, right? So when we apply the gate voltage, or when the gate voltage is less than the threshold voltage in an NMOS, right? In that case, the potential barriers between the source and drain and the channel block the current, right? So we have a potential barrier in this region that will be the blocking the current. Ideally, no current should flow. Ideally, no current should flow between source and drain, or IDS should be 0 when VGS is less than VTN in an NMOS, and MOSFET is said to be in the off state, right? But in reality, what happens is that there are some electrons in the source which are which will have high energy. Why they will have high energy? Because we know that the electrons are fermions, and they follow statistical thermal energy distribution defined by Fermi direct distribution function, right? So there will be a few electrons, less number of electrons, but few electrons will be still be there which has energy higher than the potential barrier, and they can reach from source to drain, right? They can reach by surmounting the energy barrier. So statistically, if we consider a temperature of say 300 Kelvin or the room temperature, some electrons, very few electrons or very less percentage of electrons in the source, those will have energy sufficiently high to surmount the barrier, potential barrier between the source and drain, and they will reach from source to drain despite VGS being less than VTN, right? So that leads to the conduction, and that conduction is known as the subthreshold current, right? So a small subthreshold current flow in the device even in the off state, meaning that if we apply drain to source voltage and VGS is less than VTN, small current will flow, and those will be because of the high and highly energetic electrons, and those electrons are having high energy because as they follow the statistical thermal energy distribution, that is Fermi energy distribution function, right? The now if we increase, now earlier we had seen when VGS was less than VTN. Now what happens if we have VGS greater than VTN? And also VDS is small, it is not large, right? So if VDS is less than VGS minus VTN, right, that is VDS is not large, and we had increased the gate voltage greater than the threshold voltage, then what will happen? In that case, the channel will be formed. That why the channel will be formed? Because the gate voltage was more than the threshold voltage, and therefore the channel will be formed, or electrons will be there in here, right, at the surface, right? And the channel will behave more or less like a resistor, right? So when we apply small drain voltage, or voltage between drain and source, through this channel the current will flow, and this channel will behave like a simple resistor, and we say that the MOSFET is in the linear region. So on what factors will the current depend in this state? So it will depend on the mobility of the electrons, then the Cox, or the capacitance per unit area, and the width. It will be proportional to the width and inversely proportional to the length, right? And also it will depend between VGS minus VTN, that is gate overdrive, and also the VDS. So these are the this is note that this is a first order, or the most simplest form of current equation for a MOSFET in the linear region, right? Now if we further increase the drain voltage, now we have all the gate voltage is still greater than the threshold voltage, meaning that the channel will be formed here, but now we have increased the drain voltage, right? Now as we go on increasing the drain voltage, what we expect? We expect that the voltage between gate and the drain, that will reduce, right? So voltage between gate and drain is nothing but VG minus VD. Now keeping VG, or the voltage of the gate, constant, we are increasing VD, right? So in effect VGD is coming down, right? Because VD is with a negative sign, right? So the voltage between gate and drain, that is actually reducing when we are increasing the drain voltage, right? So when VDS is greater than VGS minus VTN, then what happens is that the channel gets pinched off from the drain side. Note that on the drain, typically when we operate an NMOS, the source is grounded, right? Source is grounded and substrate is also grounded for the NMOS, and the drain is, on drain we are applying a positive voltage, right? So now when we have increased the drain voltage, so in that case the voltage between gate and the drain has reduced, while the voltage between gate and the source remains the same, right? Why? Because the source was held at the ground voltage, right? So what happens is that when drain voltage becomes sufficiently high and VDS is greater than VGS minus VTN, then the channel gets pinched off, meaning that in this region the channel get in the region in the vicinity of the drain, there the channel is pinched off, or that means that we do not have a channel, right? So the channel gets pinched off from the drain side, not from the source side, right? So the transistor will not get off, but what will happen is that the drain current does not increase with increase in the drain voltage. Note that in the linear region it was behaving like a resistor, meaning that if we increase the drain voltage, the current between drain and source will go on increasing as per the drain voltage. That is what we have, a linear resistive region or linear region in a MOSFET. But when VDS is sufficiently high, then drain current will not increase with increase in the drain voltage, and simply the pinch off point which will start shifting towards the source, right? And what we will see that the drain current is basically getting saturated, right? So that's why this region is known as saturation region, right? So the drain current will get saturated, right? Meaning that become it will not depend on VDS, right? So if we plot the output characteristics of a MOSFET, it will look something like this, right? So on the x-axis we have VDS, on the y-axis we have IDS, right? So initially, and assume that VGS is greater than, we assume that VGS is greater than VTN, right? So initially the current will increase linearly with the drain voltage, but after VGS, after the VDS is greater than VDS is greater than VGS minus VTN, the drain current will saturate, meaning that it will not be dependent on VDS, right? So even if VDS is increasing, the drain current is not increasing. So in this in as a first order approximation, in the saturation region, we can say that the saturation current depends on the mobility of the electrons in an N MOSFET or N channel MOSFET, and then capacitance per unit area, and depends on W by L, right? So if we increase the width, the saturation current will increase, right? And the gate over time VGS minus VTN whole square. Note that it is not dependent on the VDS. Then when in the saturation region, the current can increase sometimes because of what is known as channel length modulation. So let us understand what is channel length modulation. So this is a non-ideal effect in the saturation region. We just discussed that in the saturation region, the drain current becomes independent of the drain voltage, meaning that the drain current do not increase with increasing in the drain voltage, right? But what happens in the because of channel length modulation is that the drain current actually increases with the increase in the drain voltage. Why it happens? Let's understand that. So as we increase the VDS, the pinch off point extends towards the source. So pinch off starts at this point, and as we go on increasing, so we can think of that the channel becomes something like this, right? So at the source end, we have the depth of the channel is complete is high, and as we move towards the drain, the channel gets tapered, right? It gets tapered, depth goes on decreasing, and at some point it becomes zero, right? So here between this drain and this point, that is the pinch off point, there is no channel region, right? And as we increase the drain voltage, this pinch off point goes on shifting towards the source. Now as the pinch off points it shifts towards the source, the effective channel length that decreases. Why? Because this is the effective channel length between this point and this point, right? So if there was no pinch off, the channel length would have been from here to here, right? But because of pinch off, the channel length is from here to here, right? So in effect, the channel length decreases. So this phenomenon is known as channel length modulation, or change in the length of the channel. And because of this, the drain current increases slightly with the increase in the drain voltage in the saturation region also. So we can model this effect using this equation. So this is the equation that we saw for the saturation current, right? And we add one more term, 1 plus lambda VDS, to show that IDS depends on the VDS, right? So this lambda is basically channel length modulation factor. Now let us look at a few short channel effects. So these short channel effects become prominent as we reduce the channel length, right? So as with the advancement in the technology, the channel length reduces, right? So with the reduction in the channel length, what new effects can we observe will be observed in the MOSFET? So uh, ideally what we want that the gate electrode or the gate voltage at the gate terminal, that should control the fraction of or that should control the charge in the channel, right? The charge in the channel should be controlled by the gate terminal only. But as the channel length reduces, the gate electrode can control a smaller fraction of the total channel charge, and drain gets actually increased control over the channel charge, right? Which is not desirable, right? So drain, ideally we want that the gate should control the channel charge, and it should decide that when the current should flow or not flow. The drain and source ideally should act just as a contact through which the electrons or holes, that is the carriers, are injected into the MOSFET or taken out from the MOSFET, right? But as the channel length reduces, the gate control is lost, right? And the drain control becomes more prominent, right? And because of this, many non-ideal effects are seen when the channel length is reduced. So one of them is the decrease in the threshold voltage by increasing VDS, right? Typically, VTN, or the threshold voltage of a transistor, should be independent of the drain voltage, right? VDS shouldn't control the threshold voltage, meaning that the point at which the transistor starts conducting, that shouldn't be decided by the drain voltage or the drain voltage. That should be a property of the MOSFET, or that should be as per the design. By increasing the VDS, the VTN is found to decrease when the channel length is reduced, right? So this is an example of a short channel effect. This phenomenon is known as drain induced barrier lowering. Barrier here means that barrier to the flow, conduction of current between the source and drain. So the barrier is basically stopping the current between the drain and source, right? So the gate is acting as a barrier. Gate potential is acting as a barrier, right? But because of the drain, that barrier is being lowered, meaning that the threshold voltage gets lowered, or the gate or the barrier which was between the drain and source to to conduct, that barrier comes down, right? So that's why we say that drain induced barrier lowering, and that this phenomenon is more prominent when the channel length is small, right? As or channel length is reduced. As we reduce the channel length, the gate control is lost, drain control becomes more prominent, which is not desirable. And its manifestation is that the threshold voltage of the transistor is lowered by the increase in the VDS, which is again not desirable. Another effect which is prominent at when the channel length is reduced is that VTN, or the threshold voltage of the transistor, decreases with the decrease in the gate length. Ideally, the threshold voltage is independent of the gate length, gate width, and so on, right? So it is not dependent on the length and width of the MOSFET. But what happens when the channel becomes very short? In that case, the threshold voltage starts depending on the length of the channel, right? Or as the gate or as the gate length is reduced, the VTN becomes less, right? And this phenomenon is known as threshold voltage roll off, right? So this phenomenon is seen. So these two phenomenon, drain induced barrier lowering, DIBL or dibble in short, and threshold voltage roll off, these phenomenon are seen or exhibited by the MOSFETs when the channel is short, and therefore these are known as short channel effects. So for digital circuit applications, MOSFETs are used as switch, right? So it is very important to understand that how are used as switch in digital circuit application, right? So let's first look into the NMOS or N-channel MOSFET, right? So in an N-channel MOSFET, assume that the source is grounded, right? The source is grounded. So the source and the drain are basically the contacts of the switch, right? So if we consider a switch, right? So these two are the contacts, right? And when this switch will be closed or when it will be open, that will be defined by the gate voltage, right? Where the gate voltage is controlling that when it is this is one can be considered as source, other can is considered as the drain, right? Now when gate voltage is zero, this switch is off, right? We can, so in a MOSFET, when VGS is 0 volt, it is less than the threshold voltage, and therefore the MOSFET will not allow current to flow between the source and the drain, and we can consider that this switch is open, right? But when we make when we apply a voltage of VDD, or supply voltage is applied to the gate, then the voltage between the gate and the source is VDD, and it is typically higher than VTN, and therefore we can consider that the current will easily flow between the source and the drain, and we consider that this switch gets closed, right, rather than open. Now this switch gets closed, and we say that the MOSFET switch is turned on, right? Similarly, in a PMOS, let us assume that the source is connected to VDD, right? Let's assume that the source is connected to VDD, and we apply the voltage of 0 to the gate terminal, right? So if that is the case, then what is the voltage between VGS, right? VGS, in this case VGS is equal to 0 minus VDD. So gate is at 0 potential and source is at VDD, so 0 minus VDD, it is minus VDD, right? So it is more negative than the threshold voltage of a PMOS. Typically the threshold voltage of a PMOS is negative, but this minus VDD will be more negative than the threshold voltage of the PMOS, and therefore the current bit can easily flow between the source and drain, and we can consider that the switch is turned on, right? So now when we apply a voltage of VG is equal to VDD to the PMOS, then the voltage between the gate and the source will be VGS will be VDD minus VDD, that is equal to 0 volt, right? So the VGS is 0 volt and it is will be greater than the threshold voltage. Note that the in threshold voltage of a PMOS is negative, right? And therefore the current will not flow between the drain and source in a PMOS, and the switch will be turned off, right? So now to summarize, we see that in a PMOS, in an NMOS, the switch is turned on when VG is 0 volt, while in PMOS the switch is turned so in an NMOS the switch is turned off when VG is equal to 0 volt, right? And in a PMOS the switch is turned on when VG is equal to 0 volt. Similarly, or in contrast, when VG is equal to VDD in an NMOS, the switch is turned on, and when VG is equal to VDD in a PMOS, the switch is turned off, right? So the NMOS and PMOS behaves oppositely, right? So NMOS gets switched on when we apply VDD, and PMOS gets turned on when we apply 0 volt to the gate of a PMOS, right? So these two types of transistors are in a sense complementary to each other, or its functionality is complementary to each other, and therefore these two switches can be combined together to realize circuits which are known as CMOS, or complementary MOSFET circuits, right? So we'll be looking into CMOS in the CMOS inverter in the next lecture. So if you want to refer or understand more on these topics, you can refer to these references. To summarize what we have done in this lecture, we have looked into the MOSFET, the various types of MOSFETs, and why and the mechanism of operation of a MOSFET, and we also looked into a few short channel effects and how they can MOSFETs can be used as a switch in digital circuit applications. So that's it for this lecture. Thank you very much.